Today we are going to cover the topic assembly language. Now the first question over here, what is assembly language and why we need the assembly language? Suppose you want to communicate with someone. Let's say you are Bengali people. If you want to communicate with the Bengali people, need the Bengali language. If you want to communicate with the Chinese people, you need the Chinese language. If you want to communicate with the English people, you need the English language, right? So you need different language to communicate with different people of different places of the world. Similarly, if you want to communicate with the computer, you need to learn, yes, you need to learn the language of the computer so that the computer can understand your instruction. So the question is, what is the language of the computer? Zero and one, yes, they are the main two scenario of the language of the computer. By a particular sequence of 0 and 1, it creates a particular meaning, right? Now, we usually refer that term called IS, Instruction Set Architecture. Different computer has different IS, like Bangladesh has language Bengali, China has the language Chinese. So different computer hardware has different instruction set architecture. We call IS. As it defines what will be the format of the instruction, how many instructions there will be. Okay. Now, if we want to communicate with a particular machine, we need to understand the IS of the machine. From the IS, we can pick up our required instruction. This IS is not same for all the hardware. Different hardware has different IS. So different number of instructions. Okay. So that's the area we need to learn first. Instruction set architecture. Okay. Now we have found, okay, this is the IS of this particular hardware, and language of the computer is certainly binary language, like 0 and 1. So there's an instruction called, let's say, 0011 0011 0011 00. Now tell the computer 0011 0011 00 0011. Computer is happy, but are you happy? No. As a human being, it is really difficult for us to memorize a big sequence of 0 and 1. And for every instruction, there is a particular sequence of 0 and 1. As a human being, it is hard for us. A single mistake will ruin the entire effort. That means your computer will get wrong instruction and will malfunction, do wrong job. Okay. So what we do, instead of using a long sequence of 0 and 1, as a human, to make our life easier, we assign some symbols to the sequence of 0 and 1. Different sequence of 0 and 1, we give different symbol. For example, let's say, let's tell a particular sequence of a particular computer. Let's say 0 0 0 1 1 0 0 0 0 1 1 0 0. Let's say it is add A comma B. So your computer understands, okay, this is add A plus B. Okay, but for us, what we do, we assign a symbol called add. Okay, so instead of telling this long sequence of 0 and 1, we tell or we write in a language called add A comma B. Okay, add A comma B. This add instruction we understand. So the program that we write using this symbol is called assembly language. The program we write with the symbol is called assembly language. So in assembly language, we don't write the program by using the binary value 0 and 1. Instead, we use symbols for this binary value or binary sequence, so that we can easily understand and write the program. So that's the assembly language. So what we say, Assembly language has a one-to-one relationship between the symbolic language to the machine language, because for every symbol we assign, or for every sequence of 0 and 1 we assign a symbol. Okay, so there is a one-to-one relationship between assembly language and machine language, that is in 0 and 1. Now you may have a question, why we use assembly language, why not use high level language, C++, Visual Basic? They are much more easier. Okay, the question is, those high level language is not hardware specific. They really mean to make your life much more easier. For any hardware, you can use the high level language to write program quite easily, because they are more like human language, right? What's the problem? Certainly, your life is, as a programmer point of view, you can easily do the programming by high level language. Then to convert the high level language to machine code, what do you do? You use a software called compiler, because high level language is not machine specific. In general, you can write it. For all the machine, you can use the same language. But when you want to convert that high level language to the particular machine language or the particular hardware, you need to convert your high level language to that binary value or machine code. You use another software called compiler. That compiler convert your high level language to machine code. Your high level language is not machine specific, but compiler must be machine specific, so that it can generate the target code for the particular hardware, because language is different from hardware to hardware. That's why compiler is machine specific, hardware specific, but high level language is not hardware specific. Sometimes we call high level language are portable, because for all the hardware you can use the same high level language. But assembly language is not portable, it is machine specific. For different machine, you have different assembly language. Okay. So the question was, why we are using this assembly language instead of high level language? Because high level language is much more easier for the programmer to write program. It has assembly language has a particular advantage. Okay, the advantage is that over here you directly talk with the hardware. No extra code get generated when you translate assembly language to machine code. So the code you get from the assembly language become more efficient, take less time to execute, and you can utilize the hardware feature more efficiently by using the assembly language, because you directly talk with the hardware one to one. Okay, you directly talk with the hardware. But in high level language, there's no one-to-one relationship. Okay, so what happens? To do a particular job, you need to do lots of extra activity to make it generalized. For example, a print function. C++, you use a function called printf to print something. Have you ever looked at the code inside the print function? It is given in a library file. Your header file you include at the beginning, include a header file. Okay, that is given inside the header file. I have once taken a look inside the print function, and I was quite amazed that, or afraid that, how many lines of code inside the print function. Many lines of code. So when that converted to machine code, many extra code get generated that may not be required. So the code usually does not get properly optimized. But in this case, if you use the assembly language, there's no chance of an extra code. Only the required code you write, and your program become more optimized. Size of the program become less, and it run faster. So for more efficient program, okay, when time is very critical, if you want to run your program at very fastest speed, try to use assembly language program. It will generate compact code, and it will give you faster response compared to high level language. Okay, you can try it. You can download the assembler. This Microsoft assembler. You can download from the net. Nowadays, assembler are very advanced. They come with many widgets. You know what is a widget? With the click of a button, you can do the jump. Okay, so there are several widgets. There is a widget you can find called calculator. I tried it actually. I use that widget to build a calculator program in assembly language. Okay, with the click of a button, it does the job. Okay, and I have found the calculator it builds runs so fast. I compared with the calculator program that comes with the Windows. It takes much longer time than the program that has been generated by assembly language. Okay, so let's continue over here. So assembly language is a low-level programming language that is intended to communicate directly with a machine's hardware. Computer programming languages can be high-level or low-level languages. So there is a difference given side by side. For the low-level language, it is a more machine-friendly language, right? We can directly talk with the machine with the low-level language. And what is the high-level language? More programmer-friendly. You can easily write the program with less difficulty. Now, low-level language, it is more difficult for humans to understand, right? And high-level language, it is much easier to understand than a low-level language. Again, low-level language, it offers more control, allowing it to be more memory efficient because you directly talk with the hardware and you can take advantage of a specialized hardware feature directly. But in high-level language, it is also less memory efficient because it operates at a higher level of abstraction. So when there's an abstraction, sometimes when there's an upgradation of the CPU, most of the time they give some specialized hardware improvement. Okay, if you don't utilize those improvements properly in the compiler design, because those improvements should be incorporated in the compiler design. Okay, unless it is properly and efficiently incorporated in the compiler design, then the program you write in the high-level language does not generate optimized or efficient code. But that's not the issue with the low-level language or assembly language. You can directly take advantage of this specialized feature and can make your program more efficient. Now, low-level language, it needs an assembler for translation rather than a compiler or interpreter. Now, for high-level language, it is not designed to interact directly with the hardware of a computer and requires a compiler or interpreter for a translation. So, compiler basically convert your high-level language to assembly language first. Then from assembly language, it generates the machine code. Okay. So, how assembly language work? We have a scenario over here. This is the assembly language program that you have written with symbols: move, XOR, AND. These are the symbols, and these are the operand. Okay. Now, what you do, you use a software called assembler linker. Now, when you write a bigger program, you follow a special technique called divide and conquer approach. What is divide and conquer approach? You divide the bigger problem into smaller parts. Then you solve those smaller parts together, smaller parts separately. After you solve those smaller parts separately, you link all the smaller parts together to make a complete big program. That's the way your big software is developed. They are not written as a single program as a whole. Okay, they are divided into smaller modules or smaller parts, and they get solved separately, then get linked. This is called divide and conquer approach. Similar process we use in assembly language. Okay, we don't write the entire program as a single file. Okay, if it is a small program, we can do, but in most cases we follow the common procedure. That means we do divide and conquer approach. That means we divide the problem into smaller parts and write it separately. Finally, we use a software which is called linker. Finally, we link all the smaller parts together and we get the final binary or exe file. So after you assemble, you need to use the linker to get the exe file. So it will combine, linker will link or combine all the smaller parts as a whole. Okay, and finally you get the program that is purely in binary. And what is it? CPU, very happy. CPU can know that, okay, this is what to do from this code because it is in 0 and 1. And basically what CPU does, do you know? CPU only can turn on and off. You see, what is 0 and 1? 0 means off, 1 means on. Inside the CPU, there are millions and millions of switches. 100 million of switches, 50 million switches, okay? And CPU turn on and off the switch at very high rate. And that's the way it executes your instruction, by turning on and off the switch. Because an instruction is nothing but a sequence of 0 and 1. Okay? And inside the computer, you will be amazed to know that they don't do this many complex job as we see. The complex thing as we see as a result of very some simple operation. Inside the computer, what they do? It can be a register to register transfer, register to memory transfer, memory to register transfer, arithmetic operation and logic operation. Very simple things it does inside. Okay, very simple things it does inside. But doing or by combining those simple things in a particular sequence, we do amazing job or bigger job we do. Okay, and as a result, you play the video games. Okay, you watch the movie, you write a letter. Okay, you chat with your friends. Okay, and at the very basic level, your CPU is just turning on and off the switch at a very high speed. Simple job just doing. Okay, on and off only. So your CPU is a very simple device. Okay, all the complexity we give to the CPU. Okay, how to manipulate the 0 and 1, that's we give. So we are, I think, complex people, right? We are the complex person because all the intelligence people like you has given to the CPU. That's why they have designed it like that. So who is more intelligent, your CPU or you? Yes, you are certainly more intelligent because you can imagine, you can create something new. But for CPU, only follow the order. He cannot create something new. Trust me, your CPU cannot think something new. Only CPU follow the order. But as a human, you are superior all the time. Okay, you can do something new, and all the intelligence that you see, that's given by you to the CPU. Okay. So next term, yes, what is the statement? Assembler translate instruction into machine code. Each line of the assembler or your assembly language program is called statement. Now, the statement has a specific format. There are several fields. The first field is called the label or name field. Sometimes it's called label. This name field, you give the name and it ends with the colon. Usually, when you translate, this name field get converted to a memory address where this instruction is located. Okay. Now, second field is the operation field or opcode field. Over here, you write what to do. You give the instruction. What we have done over here, move. Do some movement. So, do this operation of movement. Next field is the operand field. There can be one operand, no operand, or more than one operand, depending on the need. Over here, we have two operands separated by the comma. So, what it does, usually when there are two operands, in most of the cases, the first operand is called destination. Okay, it is the destination. Okay, D for destination. I think. D for destination. And the second operand, it is called source. S for source. So in the move operation, the source data will go to the destination. Okay. The last one, which is the comment. It starts with a semicolon. Comment is not part of the instruction, but it is a very good programming practice to write comment. So let's go one by one. An assembler directive instructs the assembler to perform a specific task, such as allocating memory space for a variable or creating a procedure. Now, look at over here. This proc, when you write assembly language program, not all the instruction we write are instruction of the CPU. Sometimes you give instruction to the microcontroller assembler. You give instruction to the assembler how to handle your program. So proc is one such instruction to the assembler called sudo.
Sir, microcontroller is a part of assembly unit.
Microcontroller and microprocessor, for those two devices, you can use assembly language program to write program. They are the CPU, they are the brain. Okay. Now, for those device, we can use assembly language to write program. Okay. So when you write the program, some instructions are machine instruction. That's a part of the main instruction. Like move is the main instruction, but this proc is not the main instruction. Proc is a direction to the assembler. Inside the proc, we write our main instruction. Okay. So there are several types of sudo we use when we write assembly language programming. This is one type of sudo operation that tells the assembler define a procedure by the name main.
Sir, in Apple like CX and 5, they both combine the called as operand or
CX is one operand, 5 is another operand.
But their working principle is different. Working principle are
Okay. Now, in an instruction, there can be no operand. Suppose there is an instruction called no. I can show you at the end after the slide. N O P. This instruction no. This is an instruction, but this instruction does not have any operand because it is self-contained. No operation. It does not do anything. Another instruction can have, let's say, increment I, N, and C. Increment, let's say, X. Register or CX register. Okay. What it will do is this X, this is a single operand. Over here, you see, when we do movement operation, we see two operand over here. But over here, only one operand. So some instruction may have only one operand because it is quite enough. What it will do, it will increment the value of X register by 1. Yes, yes. What type of operation it is? Whether you need one operand or two operand, like decrement, again one operand only. Okay, so it depends on the type of operation. It can be 0 operand, 1 operand, 2 operand, depending on the instruction. So let's continue. This is proc is the assembler directive. It tells the assembler that create a procedure by the name main. Okay, so that you can write instruction inside the procedure. Now, we have told that first field that we see in an instruction is called name. Okay, so name field. When you write the name, you need to follow certain rules. Example of legal names. Let's say counter 1 is example of legal name. Add character, sum underscore of underscore digits, legal name. Done question mark, dot test, $1000, they're all legal name. Now, when they become illegal, suppose for example, 2 words. Over here, you see there is a blank space. Over here, this blank space is not allowed, contains a blank. So it is illegal. 2 ABC begins with a digit. If a name begins with a digit, it is illegal. A45.28 dot is not the first character. Okay, you see dot. If you use the dot, it should be the first character. Okay, so it is illegal. A and B contains an illegal character. So this character A and is illegal. So these are the example of illegal names. Okay. So name field is used for instruction labels, procedure names, and variable names. The assembler translates names into memory addresses. Yes? Not allowed. Only it can be the first character. Yes. But small case letter and capital case letter, they are different. Your or assembler will treat them differently. Suppose your name is Jebin, capital letter Jebin, okay? And her name is small letter Jedin. These two are different.
So what does it actually mean by illegal character?
They are not allowed. Illegal character means they are not allowed.
We can carry forward.
Here, your assembler will generate an error message if you write illegal names. They are not allowed. Okay. So when you assemble your program, it will not assemble your program. Instead, it will generate the error message. Okay, these are the mistakes in your program. Next field is the operation field. For instruction, the operation field contains a symbolic operation code, we usually call opcode. An assembler translates a symbolic opcode into machine language code. For example, opcode or operation function can be move, add, and sum. There can be more. These are some of the examples. Move will do the movement. Very good question. Move instruction will move data from one register to another register. I will show you the exact format and the uh, legal convention or legal procedure and illegal procedure of the move instruction in details. As I proceed, I'll show you all the details of move instruction. What you can do, how you write it, what is allowed, what is not allowed, I'll show you. By this time, just keep in mind, it will move data from one location to another location in the memory, inside the memory. Okay. Add will perform addition, sub will perform subtraction. In an assembler directive, the operation field contains a pseudo code that is not translated into machine code. Okay. For example, proc pseudo code is used to create a procedure, but when you assemble, this proc does not get translated. This is assembler directive, not part of the main program. Okay. Next is the that's the operation field. After operation field, this is the operand field. Okay. Operand field specifies the data to be executed by the operation. So this will be most likely to be the operand field, not operation field, operand field. Okay. So operand field specifies the data to be executed by the operation. Example. Enough. For this instruction, no operand required, does nothing. Increment x. This only a one operand. Adds 1 to the contents of x. Add word 1 comma 2. Okay. What it does, it adds the value 2 to word 1 and the result of addition gets stored in word 1. Word 1 is the source, no, destination. First one is the destination, second one is the source. Okay. So in this case, we have 2 operand, adds 2 to the contents of the memory word 1. And the result gets stored in the destination over here. So this is the destination, this is the source. Finally, is the comment field. The comment field of a statement is used by the programmer to say something about what the statement does. Why comment field is important, even though it is not part of the program? Let me tell you a small story. Suppose you are working in IT software firm, okay, and you are the programmer. You have written a program, okay, to do some specific job. After the program, you got a big salary, or I think incentive. You went for vacation, okay, college Bazaar, for 1 month. Yes. After 1 month, you have come back and you need to modify the program. During this 1 month, probably have forgotten everything, right? You enjoyed time, forgotten everything. So when you want to modify the program, you need to understand what your program does. If you don't give the comment, then it will be very difficult for you to understand the program, what it is doing. This is one scenario. Another scenario, suppose you are getting more intensive or incentive from another company. So you left your company, joined a new firm. Now in your position, a new programmer has joined and he need to work with your program. If you don't give the comment, what your program does, how the problem is solved, if you don't specify in the comment, what will happen? The new programmer will get a very hard time to understand your program. So even the comment is not part of the main program, but it is a very good programming practice to write comment. And when you work professionally, almost it is mandatory. Otherwise, in future, it will make a big problem. Okay. So how we write the comment? A semicolon marks the beginning of this field, and the assembler ignores anything typed after the semicolon. It is almost impossible to understand an assembly language program without any comment. Good programming practice dictates a comment on almost every line. For example, we have written a comment for this instruction. Move cx, 0. With the semicolon, we have written move 0 to the cx register. This is a comment. Fine, right? We can write comment in a different way. Look at over here. Move cx, 0. And we have given a comment. Cx register counts with an initial value of 0. Which one is more informative? Second one. So make sure when you write the comment, just don't give directly like this, okay? What the instruction is doing, BR operation, okay? Give the comment something that's meaningful in the context of your program.
So your CX is named as distribution, right?
Yes, definitely. So this is more meaningful. Okay, CX register counts terms with an initial value of 0. This is more meaningful from the programming point of view. So your comment should be meaningful like this. Okay. So thus the comments are used to put the instruction into the context of the program. It is permissible to make an interline a comment and to use them to create a space in a program. That means instead of like this, you can make an interline as a comment. Now, program data. In assembly language program, we may express data as binary, bit string followed by capital B or a small letter b. Decimal, a string of decimal digits followed by an optional capital D or a small d. Hex begins with a decimal digit and ends with capital H or small letter h. Characters and characteristics enclosed in a single or double quote or by their ASCII code. For example, okay, last one is the any number may have an optional sign, plus or minus. Okay, if it is plus, we don't write it, but if it is minus, we write it. So look at over here. The first number. Now tell me, this number, decimal or hexadecimal or binary? Why it is decimal? Yes. No symbol is given, okay? No indicator is given, either B or H or D. By default, if you give a write a number, your assembler will treat it as a decimal value. If you want to make it binary, then you need to write B. And then a small or capital B. Now tell me the third one. decimal. Okay. Fourth one, decimal. It has a sign. Now this one, it has a comma, illegal character. Your computer does not understand it, right? So it is illegal. Now this one, last character is H and it starts with a number. So it is hexadecimal value. 1 before D. Decimal. So this is decimal value, but what you have written? B. B is not part of decimal number. Decimal number is from 0 to 9. It does not contain A, B, C, or D. Okay. So you have given B over here. B is not allowed in decimal value. So illegal. Now this one, hex value. Why it is illegal? Because hex value must start with a number. You see? Hex value must start with a number. Over here, it will give a 0 at the big over here. Okay.
Starting number like
It can be 0 to 9, any number, depending on your need. Okay. Now, what is variable? Variables play the same role in assembly language that they do in high-level language. Each variable has a data type and is assigned to a memory address by the program. The table below shows the assembler directives that are used to define the variable. So when you define the variable, use assembler directive. DB. This assembler directive or pseudo tells that the variable that you are declaring should be the byte type variable, define byte. DW means define word. DD means define double word. DQ means define quad word, not quote. I think this will be quad. A D quad word. Okay. That means quad word means 4 words together. Okay, not quote. DT means define 10 bytes. So let's see the example. Syntax. Name, pseudo or directive, and the initial value of the variable. For example, what we have done over here, we have defined a variable of byte type by the name alpha and initialize that variable alpha with initial value 4. We have defined another variable called byt. Again, it is byte type variable, and we have given question and means no initialization. Random value can be no initialization question mark. Now, third one is that you have defined a word type of variable by the name WRD, and the initial value is -2. Now, the decimal range for 8-bit number system, okay, if it's unsigned representation, you can define number from 0 to 255 for 8-bit microcontroller. And if it's signed representation, you can define from -128 to 127 for 8-bit microcontroller. That's the decimal range, okay, for 8-bit. Now arrays, how you define the array? An array is a sequential memory bytes or words. For example, you have defined an array by the name barray, and it is byte type. That means each location can store a byte. For example, this is a memory. I think let me use the white color, right? Let's say this is a memory. Okay, so you have defined an array. At the first location, you have stored 10 hex. 10, then 20, then 30. Okay, so this is the first location, barray. This address that you see is not the It varies from computer to computer. Depending on the assembler, it gives the address. You don't need to worry about it. That's the beauty of assembly language. You just define the name. At what address it will allocate the data in memory, your assembler will take care of it. Okay, you don't need to worry about it. In this particular case, let's say BRA address is 200 hex. So at 200, you will get first element. Then on the next address, BRA plus 1. You don't need to write 201. This portion is invisible from you. This physical address, assembler will take care. You deal with this name. To go to the next element, you write BRA plus 1. You go to 20. To go to the third element, you write BRA plus 2. You get 30. Okay. So you just use the name in your program to access a particular element. Now, yes, they are the name of a particular address. In this case, name of this address 200.
So for an engineer, only policy is like
Name, you just deal with the name. It makes your life much easier. Okay, you're not you're not dealing with the complexity of the memory address or the physical address. Okay, you just deal with the name in your program. Suppose you want to access this 20, so you'll give the name BRA plus 1 for the address. So BRA plus 1 at this address, you'll get 20. Okay. Now, if you define word type array like this, word array DW, that means define word. That means every element has a size of 16 bit, 8 plus 8. Okay. So how we store this bit in memory? Look at over here. If this is your memory, okay. Suppose this is word array, first location. Each element will take 2 memory location. 0, 0, then 1, 0. There's a rule. Low order byte goes to the lower memory location. High order byte goes to the higher memory location. This is the lower memory location. In this case, it is 300. At 301, you will get the high order byte. So each element is taking 2 consecutive memory location. And how they are stored? Low order byte goes to the lower memory location. High order byte goes to the higher memory location. Okay. So if you want to access the next element 40, you need to give this address WRA plus 2 because it is word type. Okay. So let's say this is 40. Then to access the third element 29,887, you give the address WRA plus 4. To access the fourth element WRA plus 6. Okay. So when you define the data type as word, this is the way it gets stored. Low order byte goes to low memory location, high order byte goes to the higher memory location. For this definition, for this declaration, the 34 will go to the location at word 1. Word 1 plus 1, that means it will be stored like this. Same as the last slide. (34) will be stored over here. (34), okay. And 12 will be stored over here. So the address of 34 is word 1. The address of the high byte is word 1 plus 1. Right? So low byte of word 1 contains 34 hex and the high byte contains 12 hex. Okay. The low byte has symbolic address word 1 and the high byte has symbolic address word 1 plus 1. Character string. An array of ASCII codes can be initialized with a string of characters. For example, letters DB, ABC. Okay, so you define a word or string by the directive called DB. this directive db is fixed. You cannot use dw, you cannot use dd, you cannot use dt, only db. That is fixed. When you define a string or a word or a character, you use the term called db. Okay, is equivalent to letters db. This ASCII code of A, B, and C. You can check the ASCII table. If you look at the ASCII table, A is 41, B is 42, C is 44. Okay, this is ABC in the ASCII table. ABC. ABC. Okay. So you can also write like this. Same thing. Similarly, suppose you want to define a message or a string. You give the name of the string. Use the sudo dw, db, not dw. Okay, db. Only db is allowed. You write the string with a single quotation mark and some other special character. Finally, you end the string with $sign. This is mandatory. $sign is mandatory. Or you can write it in hex value like this. 48 for H, 45 for E, 40C for L, 4C for L, 4FS for O. Okay, these are the special character. And instead of $sign, what you can do? You can write the ASCII code. What is ASCII code of $sign? Can you find out from the table? 24 hex. Okay, just you can check it. 24 hex. 24 hex is the $sign. It's decimal, not hex. 24 hex. This one. Okay, this one. 24 hex. So instead of this $sign, you can write 24 hex. Okay, you can write 24 hex. Few basic instruction. Now, over 100 instructions for Intel Edge 6, especially designed instruction for advanced processor. Look at over here. For Intel Edge 6, you will find lots of instruction. For the advanced processor, again, you can find lots of more instruction. We usually start with Intel Edge 6. And for assembly language, to learn, we use a very little software, nice software. It's called Emulator 8086. If you give a search on Google Emu 8086, you can get the link and you can download the software. What I have done, I have downloaded the software. I have downloaded the software and then I have installed it. Once you install the software, you will get an icon like this on your desktop. EMU 8086. Just give a search on Google. It is free software, you can download. Okay. So after you install, you can double click. This EMU 8086 is a very good companion to learn assembly language programming. Okay. Look at over here. It has 4 options at the beginning. By clicking the new, you can write a new program. Yes, you can open the code. Code example. Yes, it comes with lots of example to have a good start. Okay. Then quick start tutor. We are interested of the quick start tutor at this point. What it does? You see, what to start? Tutorials. How to write the numbering system, what is assembly language, memory access, variable interrupts, Lots of topics required for the assembly language you can find over here that you can use. Our interest over is the instruction set. This shows you the complete listing of the instruction. If you click a particular instruction, it will show you the complete description. Okay. REG means register. SREG means segment register. Okay. Okay. Let me explain one thing over here. Let's go back to the slide and we'll explain the things to you in details. So let's first see the instruction called move. Okay. The move instruction is used to transfer data between registers, between a register and a memory location, or to move a number directly into a register or memory location. Now, if you use the software, I think it is much easier. Okay, to know about the instruction completely. So look at the sub instruction called move, MOV. LM. This is a move instruction. Click it. Okay. Now come over here. If you look at over here, move instruction, two operand, right? Destination. First is the destination. Second is the source. So what are the legal source and destination? You have the complete listing over here. So register, memory, legal. Memory, register is legal. Register, register is legal. Okay. Memory, immediate is legal. Immediate means immediate number 5, 6. Okay. Register, immediate is legal. Segment register, memory is legal. Memory, segment register is legal. Register, segment register is legal. Segment register, register is legal. So these are the valid destination and source for the move instruction. No, you cannot do. You see, you do it like this. These are the legal. Other things you cannot do apart from this. Okay, look at over here. Copy operand 2 to operand 1. The move instruction cannot. These are the limitation. Set the value of the code segment and IP register. What is code segment and what is IP? Let me just explain briefly. When you write a program and load the program in the memory, for every program your CPU allocate 4 memory locations. They are called 4 segments. The name of one segment is code segment. Another segment name is data segment, stack segment, and extra segment. In the code segment, you store the program code and instruction. In the data segment, you store the program data. In the stack segment, you store the stack data. When you call a subroutine or some other stack data you work with, you store the stack data on stack segment. The extra segment is programmer definable. That means programmer can define the use of extra segment depending on the requirement. Okay. So at a time, every program is allocated with 4 segments like this in the main memory. In Intel 8086, memory size is 1 megabyte and the segment size is 64 kilobyte. Every program will be given this 4 segment to store instruction and data and other information. Okay. And the segment is like code segment register, what's the address of the segment in memory. And instruction pointer, what is the offset of the instruction in code segment. Just something like this. If I draw a picture over here, let's quickly draw the picture. Let's say this is this is 64 kilobyte code segment. Okay. Start of the segment, end of the segment. Okay. That's a 64 kilobyte in total. So code segment register in the CPU will hold the starting address. Okay. And the IP, let's say your instruction that you are going to execute on the next clock cycle. Okay, IP register will hold this offset or address distance. IP. Okay, so IP instruction pointer register will hold this offset. So by using the content of code segment plus the IP, you can access the instruction that you are going to execute on the next clock cycle. So IP always holds the address of next instruction to be executed. Universal truth. For any CPU, IP always holds the address of next instruction to be executed. So how it works? Code segment and IP works together. Code segment holds the starting address, and at the offset of IP, you get the instruction. Okay. So let's go over here. So these are the limitation of the move instruction. Set the value of code segment IP register. Move instruction cannot do it. Copy value of one segment register to another segment register not allowed. Should copy to general register first. Copy immediate value to a segment register not allowed. Should copy to general register first. Okay. So this is the algorithm. Operand 1 gets the operand 2. And these are some example. And it does not affect any bits in the flag register. Okay, it doesn't affect any bits in the flag register. Look at the this is the flag register: carry flag, zero flag, sign flag, overflow flag, parity flag, auxiliary carry flag. No flag bits are affected. Next instruction we have seen is the exchange. This one. Let's click it. So these are the valid format. Destination can be register, memory, or register, and source can be memory, register, and register. These are the valid combination of source and destination. So what it does, it changes values of two operands. This is the algorithm, and these are some example. And it does not affect any flag bit. Okay. Our next instruction is the add instruction. The add and sub instructions are used to add or subtract the contents of two registers, a register, a memory location, or add and subtract to and from a register or memory location. This is the format: add destination comma source or subtract destination comma source. So if we go to the software, we have the complete description. Just click the up button. This is the add instruction, ADD. Okay. So this is the way it works. This is the valid combination of source and destination. And this is the some example. And it affects all the flag bits. Add and sub instruction affect all the flag bits. So here is the sub instruction. A sub. Okay. And this is a valid combination of source and destination. It subtract source from the destination, and the result get stored in the destination. Now see, it affect all the flag bit. It affect all flag bit depending on the operation. Okay. Next is the negate. Negate energy is used to negate the contents of the destination. Negate does this by replacing the contents with its 2's complement. For example, negate destination or negate dx. That's the job. Also, you can check it over here. NEG. Go to the top. Negate. Okay. It affects all the flag. It affects all the flag. And this is the valid. I think only one operand over there. Only one operand. It can be register or memory. So next slide. Program structure. Assembly language program occupies code, data, and stack segments in memory. The same organization is reflected in assembly language program as well. Code, data, and stack are structured as program segment. Program segments are translated to memory segments by the assembler. Now, this is a memory model. When you write a program in assembly language, there are several memory models. The size of code and data a program can have is determined by specifying a memory model using the dot model directive in the form as follows. Dot model, you give the name of the memory model. So this memory model can be small, means that code in one segment, data in one segment. So as you recall that for every program, 4 segment is allocated. For every program is allocated with 4 segments: core segment, data segment, stack segment, and extra segment, right? So in a small model, code in one segment, data is another segment. Okay. In medium model, code in more than one segment, data in one segment. Compact, code in one segment, data in more than one segment. Large, code in more than one segment, data in more than one segment. That's a large model. And no array larger than 64 kilobyte. But if the model is huge, okay, code in more than one segment, data is more than one segment, arrays may be larger than 64 kilobyte, okay, that's the huge. So this is the data segment. A program's data segment contains all the variable definition. Constant definitions are often made here as well, but they may be placed elsewhere in the program since no memory allocation is involved. The data directive is used to declare a data segment. Look at over here. This is the data directive. Dot data. Tells that in this data segment in the memory, this data will get stored, and you declare it over here. You have defined word 1 is with value of 2, word 2 with a value of 5. Message have defined this is a message, and you have used a constant. For the constant, you use the pseudo called equate. Okay, equate is the pseudo that gives a name to a constant. So let's say this is the constant, and if I have given a name called marks over here. So instead of writing this longer value, you can use the name in your program. It has some advantage. Suppose you have written a program about this class. This semester we have 40 students. Next semester maybe 45. Last semester it was just 35. So different semester, different number of students. If you use this student number at 100 place of your program, 100 times in student, instead what you can do, you can define a constant name. Let's say student number equate 40. Just one line at the beginning. Then at 100 location, just use the name. You don't need to change 40 at 100 location, or you don't need to write 40 at 100 location. Use the name in your program with a generous. You don't need to change the program, only change the declaration. Number of students equate 40. This semester or the next semester, number of students equate 45. Just change the value in one location of the constant. Every place it will take effect. Yes, you need to follow the naming convention. Naming convention, okay? Yes, naming convention for the name. But use the pseudo called equate, EQU. This is the pseudo or assembler directive. Okay? And it does not occupy any memory. Now, stack segment. The purpose of a stack segment declaration is to set aside a block of memory, the stack area, to store the stack. The stack data area should be big enough to contain the stack at its maximum size. So whatever is the maximum size or the required size of your stack in your memory, you should allocate that size for the stack, right? So for example, dot stack 100 hex. So you have defined a stack size of 100 hex. If the size is omitted, that means if you just omit this size, then by default 1 kilobyte is set aside. In that case, 1 kilobyte will be set aside by default. Now, the code segment. The code segment contains the program instruction, and this is the syntax dot code name. Inside a code segment, instructions are organized as procedure. How to declare the procedure? Proc, and this is the name. This is the start of the procedure, and at the end, nproc, np. Okay, with the name. This is the syntax. So the last line in the program should be the end directive, followed by the name of the main procedure. In a program, usually you write a main procedure, right? As you write in C++ or C, main function. Similarly, in a program, you write a main procedure. So at the end of the main procedure, you need to give the end directive.
So here main function runs like main procedure.
Yes.
In C++, we learn about main function.
Yes. Similarly, main. Okay. Similarly, over here, you can write a procedure like a main, and from the main, you just call the subroutine or other function. Okay. So look at over here. This is a general format of dot model program over here. Dot model is small, code in one segment, data is another segment. So you define the struct segment, initialize with 100x. You define the data segment. You can do the data definition over here. You define the code segment. You define the main program, of the main program. Finally, in main. Okay, this is the general format of the assembly language program. Now, there are some specialized instruction called input instruction and output instruction. Input instruction takes data from the outside world, and output instruction sends data to the outside world. And if you look at the example over there, in out, okay. So go at the top, find out in. Get over here. Input from port into AL or AX register. So you give the port address over here, source, and finally you can take data in the AL register or AX register. And it does not affect any flag. And what is the output instruction? Click output. OUT out, okay? That's the output instruction. Output from AL or AX to your port. And this is the syntax. Also, it does not affect any flag. Okay. In and out instruction to access the ports usually used directly when fast I/O is essential. Seldom used as port address varies among computer models. Easier to program I/O with service routine. Okay, when you do the I/O, it's easier to work with the interrupt service routine. And we'll show you how to use the interrupt service routine. So I/O service routines and interrupt 21 hex. What are the different types of I/O service routine? It can be the BIOS routine, interact directly with the ports stored in ROM. It can be the DOS routine, carry out more complex tasks, for example, printing a character string. I/O service routine. The basic input-output system or BIOS routine. The DOS routine. The interrupt instruction is used to invoke a DOS or BIOS routine. Okay. Interrupt 16 hex invokes a BIOS routine that performs keyboard input. Interrupt 21 hex may be used to invoke a larger number of DOS functions. And if you go over there, you have a complete listing. Interrupt. There are several interrupts. They have different functionality. Every interrupt has a number. And in our programming, we most widely use the interrupt 21 hex. Okay. For example, suppose you want to read a character from the keyboard. Then what you do? Very short code. You give the function code in the AS register and call the interrupt function 21x. Then it will allow you to read a character from keyboard. Suppose you want to write a character to the output device or display. Give the function code 2 in the AH register. 2 is the function code. Then the character you want to display, ASCII code you place in the DL register. Then interrupt 21x will display the character on the display. Suppose you want to output character to printer, function code is 5. Function code 6, direct console input or output. Function code 7, character input without echo to DL register. Function code 9. Okay. Suppose you want to print a string on the monitor. So use the function code 9. So this is the way to print a string. Hello world. This is the first program you usually do with assembly language. Okay. Print a message hello world on the screen. So this is the program for it. And in assembly language, this is the way to do it. Function code is number 9 in the AS register and call interrupt 21 hex. Okay. And you supply the offset or address of the string the DX register. Job is done. So let's go back. Jump instruction. Now there are several types of jump instruction. Okay, look at over here. Several types of jump instruction. Jump if 0, jump if not 0, jump if carry, jump if not carry, jump if overflow, jump if not overflow. Okay, several jump instruction, and the best way to look at it, come over here. Start from jump instruction set. So look at the jump J. Okay, JA, JE, JB, JBE, JC, JCX,
So J is
basic one. Jump is the basic one. Okay, so it is unconditional jump. Transfer control to another part of the program. Okay, this is the instruction format. Jump, you give the 4-byte address or label. Okay, and this is an example. It does not affect any flag. So there are different type of jump instruction. If you're interested, just check it over here. Okay. Finally, compare instruction. Compare instruction, compare to operand. How it works? Look at over here. Compare. No. Look at the different instruction. Like compare instruction, it affects all the flag. You see? Compare. Compare instructions subtract operand 2 from operand 1. But the difference from subtraction is that it does not store the result in operand 1. Compare instruction does the subtraction, but does not store the result of subtraction in the operand 1. Only does the subtraction. Okay, and it affects the flag register. So by checking this flag bit, we can tell whether they are equal, less, or greater than. Okay, so compare instruction. Result is not stored anywhere. Flags are set. All the flags are set according to the result. So by checking the flag bit, you can tell whether one number is less or greater than or equal by checking this flag register. So that's the compare instruction. Okay, and there are different type of jump. Jump is greater. After comparing, if you know that, okay, if AX is greater than BX, then you can use jump greater if greater. Then jump JG, jump if greater than, transfer to below. Go to the location below. Below is the address or name. Decrement X. If the contents of X is a signed sense is less than 0, okay, jump if less than. Control transfer to location 3. Okay, jump if below or low. JL. So it has different syntax. So jump based on unsigned comparison. Okay, there are different instruction. All the details you can find from the software, and jump based on signed comparison. Signed versus unsigned jumps. Look at over here. A program has been given. Suppose AX and BX contains signed numbers. Write some code to put the biggest one in the CX register. Okay, so the code is given over here for you to practice with. The jump instruction. Okay. Finally, we have shown some logical instruction and or XOR instruction. They perform logical operation. Okay. The detailed description again is you can find I think on the software. This is the AND instruction can be used to clear specific destination bits while preserving the others. A 0 marks bit clears the corresponding destination bit. A 1 marks bit preserves the corresponding destination bit. So this is an operation. Okay. So clear the sign bit of AL while leaving the other bits unchanged. So use this and AL comma 7FH. So this yes, logical operation. Okay. So these are some of the specific uses. Okay, with an operation. Set MSB and LSB of AL while preserving the other bits. So you can use the OR operation like this. Or L comma 81X. Change the sign bit of DX. Then you can do XOR operation. XOR DX comma 8000X. It will change the sign bit of DX. Converting an ASCII digit to a number. So you can use this procedure. If the 5 key is pressed, L gets 35 hex instead of 5. So to get 5 in L register, we could do this. Subtract L comma 30 hex. So this is some of the tricks you can use to perform your activity. Okay, for MCQ, you need to understand, and from your best understanding, you can easily write these things. Okay. Now, to convert from a small case to capital case letter, you see, a small trick you can use over here. For example, if DL contains the code of a lowercase letter, we could convert the to uppercase by executing sub DL comma 20x. Okay. Okay. So very simple trick you can use to convert from lowercase to uppercase and uppercase to lowercase. Clearing a register, you can use this trick: move x comma 0, then subtract x comma x. Okay. Some of the quick trick has been shown over here to make your programming easier. Testing a register for 0, you can use OR cx comma cx. Some of the uses of logic operation. Okay. Test instruction you can use. Test destination source. Okay. Not instruction. Complement the bits in a register. You can use the not instruction.
So why is important for
Look at over here. Performs an on operation but does not change the destination content. For example, test destination source. The purpose of test is to set the status flag. The purpose of test is to set the status flag. Examine bits. You can use this test instruction to examine the bits in the flag register. Okay, look at over here. Test. Logical and between all bits of two operands for flag only. These flags are affected. Okay, 0 flag, sign flag, parity flag. Result is not stored anywhere. So to check the status of the flag, you use the test instruction. Okay. Shift and rotate instruction. For a single shift or rotate, the form is opcode destination comma 1. Opcode destination comma CL. Okay. So these are the some of the example. ASL, this is the shift left, and shift right HSR. Okay, you can find this is the shift left. ASL is the shift left. Go over here. H shift. Okay. H is shift left. shift right, okay, shift left. Shift operand 1 left, the number of shifts is set by the operand 2. Okay, and what is shift right? Same thing on the right side. Shift operands right, operand 1 to the right. Okay, first operand to the right, the number of shifts is set by the operand 2. How many shifts you will do? Okay, finally, what are over there on our multiplication and division? Okay, so for multiplication and division, you see, come over here. Okay, multiply. Also, there are another type of multiply I think you can find. I multiply, okay? It is the sign multiply. That is a multiply is assigned. If you do the sign multiply, then you can use I mul, sign multiply. And this is the format, the way it works. This is the upland, okay? Register memory, and this is the example. It affects some of the flag register. Okay. So this is a division instruction again. A division instruction is used to divide, and that's the end of the slide. So what I strongly suggest with this slide, use the software IMU Intel 8086. Okay, because with that software, you have the sample code over there and detailed description that is not present in the slide. Okay, so make sure just give a search on Google IMU 8086 with a name. Okay, EMU. Let me write it over here. IMU. Okay. E M U Okay, just type in Google search engine IMU 8086. You can find lots of websites that have this software. You can download from them. And best part, go to the help file, quick tutor. Okay, there's a quick tutor. So as you go with the slide, use this software. Practice in the software directly, because every instruction has a sample code over there. Take the sample code, write the program in the software, verify it. That's the best way to learn assembly language programming. In one day, it cannot be expert. Over the time, as you practice, day by day, you will be the expert. Okay, so we have covered a big topic in a single class, but as you practice, as you do more work on it, you will be more expert on it. Okay, so good luck to all of you, and this is the end of our class for today. Let me take the attendance. Okay.